Right, let us give you some help with motion and forces questions. These are taken from a foundation paper, but they'll be good for higher tier candidates as well, because there's always an overlap. And you can see this is a popular topic because there's 57 marks being asked recently about it over the last few exam papers. Right, question 1. An aircraft waits at the start of a runway. The aircraft accelerates from a speed of nothing, so that's u, our starting speed, to a speed of 80, so that's v, our final speed, or final velocity. The acceleration of the aircraft is 4 meters a second squared, so that's a. Calculate the distance x travelled by the aircraft while it's accelerating and use this equation. Right, we've just basically got to pop the numbers in. So that equals 80 squared, take away 0 squared, divided by 2 times by the acceleration, which was 4. And that's going to come out as 800. And it's distance, so that's meters. Question 2. A car with a mass of 1,800 kilograms is accelerating at 1.2 meters per second squared. Calculate the force used to accelerate the car. Do you see what I'm doing here? Every time that it tells us something, I'm writing down the symbol for that thing. So we've just got to pop the numbers in then to get the force. We'll do the mass, which was 1,800 kilograms. Times that by the acceleration, which was 1.2 meters per second squared. And that comes out as 2,160. And it's newtons because it's a force. Question 3. Figure 7 shows a skier going down a hill. Describe how her speed at the bottom of the slope could be determined. Right, well, base your explanation on the calculation. So the calculation for speed is speed equals distance divided by time. So in order to calculate the speed, we're going to need to measure the distance, say what you're going to use to measure it, like a trundle wheel, and you're going to measure the time. So say what you're going to measure that with, i.e. a stopwatch. You could possibly get 4 marks for that. Now they are saying measure it at the bottom, so you could say put a marker here and put a marker there. So that's your first marker, and that's your second marker. And you could say start your stopwatch when the skier hits the first marker and stop the stopwatch when the skier hits the second marker. Question 4. Which row of the table is correct for both force and velocity? Right, well, they're both vectors. They've both got size and direction. So the answer's D. Question 5. A toy has a mass of 0.1 kilograms. The toy accelerates at 2 meters per second squared. Calculate the force producing this acceleration and use the equation. Now you'll notice it's the same questions coming up again and again. That's because I've taken all of these questions from different papers. So you can see they like to use the same questions each year. So do the mass, 0.1 kilograms, multiply that by the acceleration, which was 2 meters per second squared, and that just comes out as 0.2, and that'll be newtons. You see this year they've gave you 3 marks instead of 2, and they haven't told you what the units are. Question 6. Which of these situations can increase the reaction time of a driver? Put a cross next to the box. Icy road, no. Worn tyres, no. Stopping for a cup of coffee, no. Driving for a long time without a break, yes. That could make your reactions slower, which means your reaction time would increase. So the normal reaction time is 0.25 seconds. If your reactions get slower, your time could increase to 0.5 seconds. Part B1. A car engine produces an average driving force of 1200 newtons. The car travels 8 metres, that's the distance. Calculate the work done by the force over this distance. So work done gets called E, because energy transferred is the same as work done. And the equation is work done, or energy transferred, is force times by distance. So you just multiply the two together. So that's 1,200 newtons times by 8 metres, which is 9,600, and that'll be joules, because work done is in joules. Part 2. The car has got a mass of 1,400 kilograms and travels at a velocity of 25 metres a second. Calculate the kinetic energy of the car. Right, so the equation for kinetic energy is a half times by mass times by velocity squared. So let's just pop the numbers in. So that's a half times by 1,400 kilograms times by 25 squared. That's meters per second, and that's going to come out as 437,500, and that'll be joules. Question 7. Which of these would be a typical speed for a racing cyclist travelling down a steep straight slope? 0.2 metres a second, not too slow. 2 metres a second, not too slow. 20 metres a second, that seems right. Just look at the last one, 200 metres a second. Nah, that's far too big. So C was definitely right. A cyclist travels down a slope. The top of the slope is 20 metres vertically above the bottom of the slope. The cyclist has got a mass of 75 kilograms. So D was the, or rather H is 20. Calculate the change in gravitational potential energy, so that's GPE, of the cyclist between the top and the bottom of the slope, and it tells you that gravity on Earth is 10. So the equation for gravitational potential energy is mass times by gravity times by height. Or they sometimes say change in height if you are getting a change in gravitational potential energy. So just pop the numbers in. 75 kilograms times by 10 newtons per kilogram times by the height, which was 20 metres. And that comes out as 15,000. And that's joules. Question 8. Figure 1 shows a speed time graph for a car. So speeds up the side, times along the bottom. Part 1. The graph in figure 1 is divided into 4 parts, P, Q, R and S, P, Q, R and S. Draw a line from the letter for each part to the correct description of the motion during that part. One line's been done for you. So at P, the car is accelerating because the speed is increasing. So that goes with that. It already says that Q is the car travelling at a constant speed, so a constant speed of 30. R, the speed is decreasing, so that's decelerating. And at S, the car has stopped at 0. So S, the car is standing still. Part 2. In two parts of the graph in figure 1, the forces are balanced. State the letters of the two parts of the graph where the horizontal forces acting on the car are balanced. Right, well, if the forces are balanced, that means it's either not moving or it's moving at a steady speed. So it was not moving at S and it's moving at a steady speed at Q. So the answer is Q and S. Part 3. Calculate the distance travelled by the car in part Q. Use the equation distance travelled equals average speed times by time. So if we go back to the graph, the average speed, well, was 30 for this section here. And the time went from 50 up to 150. So that time was 100 seconds. So average speed was 30 meters per second and times that by the 100 seconds. So that is 3,000 meters. Question 9. Figure 1 shows a block hanging from a spring balance. Use a word from the box to complete the sentence below. The quantity measured by the spring balance in figure 1 is, well, it'll be the weight because it's hanging like that. Question 10. Sam and Joe are on their bikes. They are on a flat, straight road. Joe is stationary when Sam rides past at a constant velocity of 10 meters a second. Joe waits for 4 seconds and then follows Sam. This is a velocity time graph of their motion. Part 1. How far did Sam travel during these 15 seconds? So to get the distance, you do velocity times by time, and that's for Sam. So you can see conveniently his speed is constant, so that's 10. So his velocity is 10 meters per second, and he travelled at that speed for 15 seconds. So if you multiply that together, that's 150 meters, which is answer D. Part 2. At which of these times is the resultant force on Joe bigger than the resultant force on Sam? Well, if Sam's travelling at a constant speed, that means that his resultant force is 0. And if you aren't moving, the resultant force is 0. And if you are travelling at a constant speed, it's 0. So the only time when Joe actually had a resultant force on him was when he was accelerating. So that is between the time here and here. So what's this? Is this 4? So that's 1, 2, 3, 4, yeah. So between 4 seconds and 10 seconds. So what's the options? 3 seconds, nope. 7 seconds, yes. 11, no. 15, no. Right, so the only time between 4 and 10 is this option here, B, 7. Part 3. For how many seconds was Joe accelerating? Oh well, between 4 and 10, so that was 6 seconds. Part 4. Calculate Joe's acceleration during this time. Okay, so acceleration equals the change in the velocity divided by the time. So let's have a look back on the graph. And Joe's velocity went from 0 up to 15. So he's changed by 15, and it took 6 seconds to do that. So it changed by 15 meters per second, and it took 6 seconds to do that. And that equals 2.5 meters per second squared. Because that's meters per second, or meters per second squared is how we simplify it. Part B. The diagram shows the horizontal forces acting on Joe at one point while he's accelerating. The backward force is 30 newtons, the forward force is 100 newtons. Calculate the size of the resultant force acting on Joe and his bike. Okay, if it's a tug of war, this team's pulling forwards with 100 and this team is trying to pull backwards with 30. So the resultant is just who's won and by how much. So the size of the resultant force will be 100 take away 30, which is 70 newtons. And that'll be forwards. Because force is a vector, so technically you should be putting the size and the direction. Part 2. The total mass of Joe, his heavy bag, and his bike is 55 kilograms. That's the mass. Calculate the total weight, and it tells you that the gravitational field strength G is that. Okay, so you're supposed to know that weight equals mass times by gravity. Pop the numbers in. 55 kilograms of mass times by 10 newtons for every kilogram, and that's going to come out as 550 newtons. Part C. On another day, Joe is riding the same bike on the same piece of road. This time he does not have the heavy bag on his back. He finds that it's easier to accelerate. Explain why Joe finds it easier to accelerate. Well, from Newton's second law, force equals mass times by acceleration. So force, mass and acceleration are all linked together. If something doesn't have as much mass, then you don't need as much force to make it accelerate. Or if he does use the same force on a smaller mass, the acceleration will be bigger. Just think about if you're pushing a friend on a sledge. If you've just got a little friend, then your force will make the acceleration big. Whereas if you've got the sledge and you've got a great big friend, that's got a big mass, for the same amount of force, the acceleration will be small. Sledges have got little things on the front, haven't they? That's how I explain it to my students. Question 11. The distance time graph for a car is shown below. Describe what the graph shows about the speed of the car as it travels the 80 metres. Right, well, when I'm looking at the graph, it's sort of two sections. So at first, this section is constant, and then it's not as steep anymore. So this steep slope means they're travelling fast, and then the flatter slope means they've slowed down. So at first, the slope is steep, so speed is fast. Then the speed slows down. Then the speed slows down because the slope is flatter. To be honest, you'd probably be okay just putting what I've underlined. And remember, the slope would be distance divided by time, which gives us our speed. Alright, your teacher might use the word gradient instead of slope. Question 12. Some students investigate the speed of cars. They measure the time it takes each car to travel a distance of 80 metres. State 2 measuring instruments the students should use. Right, we'll measure time with a stopwatch. And measure the distance with a trundle wheel. Part B. The table shows some of their results. State the colour of the slowest car. Right, well, they're all travelling 80 metres, so they're all travelling the same distance. So basically, the slowest car will be the one that takes the longest time, which is the white car. Part 2. Calculate the speed of the black car. So there's the black car there, and it travelled 80 metres in 4.3 seconds. So speed equals distance divided by time. So that's 80 metres divided by 4.3 seconds. And that comes out as 18.6 metres per second. Part 3. 20 miles per hour is approximately 9 metres a second. Estimate the speed in miles per hour of the black car. Right, the black car is basically twice as fast as 9, isn't it? If you take 9 and double it, that's 18. So that's roughly going to be 20 times by 2, which is 40 miles an hour. Question 13. Which of these speeds would be normal for a person walking? 0.1 metres a second? Nah. 1 metre a second? Yeah, that's about right, isn't it? You take 1 step per second and each step is about 1 metre. So there we go. 10 or 100? Nah. Far too big. Question 14. The chart shows the thinking, braking and stopping distances for an average car and driver stopping from 50 miles per hour as shown in the highway code. It also shows the thinking, braking and stopping distances for drivers of cars A and B, both stopping from 50 miles per hour. So they're both going at 50 miles per hour. A and B are different cars on different roads. Use the factors that can affect thinking and braking distances to explain the differences in stopping distances for cars A and B. Right, well, if they give you the data, I always like to use it. So car A their thinking distance is about 22 metres. And car B, their thinking distance is about 12 metres. And then their braking distance for A, right, that goes from 22 up to about 55. So that's 23 metres. And the braking distance for car B goes from 12 to about 71, so that's 59 metres. So we'll probably get some marks if we just quote those values, and then we'll say for 6 marks why they differ. So factors that affect the thinking distance are drugs, alcohol, distractions. They will make you take longer than normal to react. So car A has a longer thinking distance than car B. And we'll pop the values in. Just in case they don't see our annotations on the diagram. Now we'll say why. This will be because of a longer reaction time. And the reaction time will be longer because of drugs or alcohol or distractions. Such as using a mobile phone. Right, now I'm actually going to put that down as thinking distances. Now the reasons for braking distance so let's have a look. So car B's braking distance was longer than car A's braking distance. Now that'll be because of factors to do with the car. Car A must have better brakes or better tyres, or maybe they're driving on a dry road, so they're not going to skid. So car A's braking distance is shorter than car B's. Let's pop the numbers in just in case once again. This means car A might have better brakes, tyres, or is driving on a dry road so it doesn't skid. And then overall, let's talk about the total stopping distance. So car A, the total stopping distance is 55 metres, and car B, the total stopping distance is 71 metres. Right, we'll easily get 6 marks for saying all of that. Question 15. A student needs to measure the average speed of an accelerating trolley between 2 marks on a bench. Figure 5 shows the arrangement of some apparatus that the student can use. One piece of apparatus is missing from the diagram. This piece of apparatus is needed to determine the average speed. State the extra piece of apparatus needed to determine the average speed. Right, base your explanation on the calculation. So to get the speed, you need to do the distance divided by the time. We measure time with a stopwatch, which is in the picture. We measure distance with a ruler, which is missing from the picture. So that's what we need to say. Part 2. Describe how the student can make the trolley accelerate along the bench. Right, well, the trolley is connected by a string, and we'll put some masses onto this hanger, and then we'll put the hanger on the end here and just basically drop it. So that force of it dropping will pull the trolley. Hang masses on the end of the pulley. Drop it to pull the trolley because it will apply a force to the trolley. Part 3. The student wishes to develop the experiment to determine the acceleration of the trolley. State one other measurement that the student must make to determine the acceleration of the trolley. Well, to get the acceleration of something, you need to know the change in velocity. Divide that by the time taken for the change. Now the change in velocity is going to be the final velocity v, take away the initial velocity u. So in order to get the acceleration, we're going to need to measure the change in the velocity. We need to measure the velocity at the start and at the end. Or you could say the time between the two velocities. And finally, question 16. Use words from the box to complete the sentences below. Vectors have size and direction. Scalars have only size. There you go. Hope that's helpful. The more you practice, the better you get. Simple as that. There's lots more videos on my channel that will help you to pass your exams. Good luck, work hard, be nice, and bye for now.